Hey everybody, Mr. Bucko here with examples for Power Standards Quiz 40 to 43. First example that I have up on the screen here, we are finding the product of two binomials. Binomial is an expression with more than one or two terms in it, so we have r and -9, and this other binomial has r and a +2. And we're going to multiply them because product means we are going to multiply. And how we're going to go about doing this is using the distributive property. We're going to distribute each of the terms in the first binomial by each of the terms in the second binomial. So the first thing I'm going to do is take a look at this r, and I'm going to distribute the r, meaning I'm going to multiply the r by each of the terms in the second binomial. So I'm just going to distribute. So I'm going to do r times r. And r times r is r squared. And then, to continue that distribution, I'm going to do r times 2, and r times 2 is 2r. Now I'm done distributing the r, and now I'm going to distribute this -9. So the same exact process, but now I'm going to multiply all of the terms in the second binomial by -9. So now I'm going to do -9 times r, which is -9r. And then I'm going to do -9 times 2, which is -18, because a positive times a negative is a negative number. Now I've done that multiplication, the parentheses are gone. Now I'm going to combine like terms if applicable, and I can because I have a pair of like terms here, which are the 2r and the -9r. And 2r minus 9r is -7r. So what I have now is our simplified product, r squared from right here. The -7r comes from 2r minus 9r, and minus 18 from here. So the product of this multiplication gives us r squared minus 7r minus 18. Next example, we're looking for greatest common factor. Greatest common factor of 5x to the 7th and 15x to the 4th. And to show how we go about finding the greatest common factor, I'm going to break these terms down as much as I possibly can. So when I look at 5 times x to the 7th power, what that is 5 times 7x's. There are 7x's here, and this right here is 5x to the 7th, just expanded, written out. Everything's kind of broken down. It's the prime factorization of 5x to the 7th. I've broken it down as small as I can go. I can't break down 5 anymore into integers because 5 is a prime number. I'm going to do the same thing with 15x to the 4th. 15x to the 4th can be written down or broken down into 5 times 3 because 5 times 3 is 15. And then we have x times x times x times x because that is x to the 4th. So on the screen here now I have the prime factorization of 5x to the 7th and 15x to the 4th. I've just broken them down as much as I possibly can. I can't break these things down anymore. 5 can't be broken down because it's prime. Also 3 cannot be broken down anymore because that's a prime number. So now that I have this, it's going to be easy to see what they have in common. What do these two have in common? The first thing they have in common is a 5. They both have a 5. So a 5 is going to be in the common factor of this. What else do they have in common? They don't have a 3 in common, so that's not a part of the greatest common factor, but they do have some x's in common. How many x's do they have in common? Looks like 4. Each term has at least 4 x's. So therefore, the other part of this greatest common factor is x to the 4th. So therefore, the greatest common factor of 5x to the 7th and 15x to the 4th is 5x to the 4th. And lastly, talk about rational and irrational numbers. Just a quick summary of what each of these things are. Rational numbers are numbers that can be expressed as a fraction with an integer numerator and denominator. And we're going to take that definition and kind of throw it out in a minute here. Irrational numbers are numbers that cannot be expressed as a fraction with an integer numerator and denominator. So those two are the technical definitions of rational and irrational, but how we identify these things will not really be using those definitions. When we talk about rational numbers, a rational number is a number that can be expressed as a fraction or a whole number. So I have the square root of 25. The square root of 25 is a rational number because the square root of 25 is 5. We know what it is. It's an integer. It's 5, and we're done. An irrational number would be the square root of 26. And the square root of 26 is an irrational number because 26 is not a perfect square. So to tie this into the definition, the square root of 26 cannot be expressed as a fraction. It's a decimal, and it goes on forever, and it has no pattern to it. So therefore, the square root of 26 is an irrational number. I don't know what that number is exactly. I don't care what that number is. But I know that the square root of 26 is an irrational number because 26 is not a perfect square. So that would be an irrational number, and that's how you're going to see irrational numbers, because you can't write out an irrational number because it doesn't end. So irrational numbers need to be written with a symbol, like the square root, and we call it the square root of 26. Another rational number would be square root of 81 plus 6. Why is this a rational number? Because I know what the square root of 81 is. It's 9. So this number right here is really 15. The square root of 81 is 9, therefore it's a rational number. An irrational number would be the square root of 76 plus 1. Why is this an irrational number? Because 76 is not a perfect square. I don't know what the square root of 76 is because it's not a perfect square. And even if you take an irrational number and you add a one is a rational number, but even if you add a rational number to an irrational number, it still stays irrational. So this would be an irrational number also. Another rational number would be the square root of 12 times the square root of 3. But you might say, well, 12 and 3, however, are not perfect squares. So how can that be a rational number? Because if we have a square root times another square root, we can multiply those numbers in the square root together. So the square root of 12 times the square root of 3, that's the square root of 36. And it's rational because I know what the square root of 36 is. It's 6. But if we have, let's say, the square root of 12 times the square root of 4, that's also an irrational number. Although you might say, well, wait a second, the square root of 4, I know what that is. But it's the square root of 4 times the square root of 12. So if you multiply those together, you get the square root of 48. I don't know what the square root of 48 is because 48 is not a perfect square. So therefore, the square root of 48 is an irrational number. And another rational number, 17. A whole number. It's an integer. It ends. And another irrational number, the most common irrational number that we've seen up until this point, is pi. Pi is an irrational number. And once again, irrational numbers need to be written with symbols because they're decimals that go on forever. You can't write a decimal that goes on forever and say that it's irrational because you have to stop at some point. So we have to use symbols. So the symbol pi is an irrational number. Also, any square root of a non-perfect square is also an irrational number.